Okay, so homework 12 is due next Thursday, so 1 week from today. There are a lot of problems from chapter 7. These, again, are very similar to what we've already done. Okay, you're using property tables, you're calculating efficiencies, you're making assumptions based on what you know about a process in order to calculate or find the entropy. So don't overly complicate things that should be straightforward and things you should know how to do. Okay, so like with this entropy problem, there are some interesting applications for some of the equations that we learned already about entropy, but please remember that it's also a property value, and you can use the tables to look it up, to calculate, to find entropy changes and things like that. So today we're going to talk about special conditions of isentropic processes and how the property diagrams can actually be quite useful to us to see how irreversible a system or a process is. So what is entropy? By way of review, that it's just useful to us in second law analysis because it tells us how irreversible a system is. And we view it as disorder or randomness, which contributes to inefficiencies in real systems. We talked about how substances at higher energy states will have a greater degree of disorder. So if you think about gases versus liquids versus solids, that as these molecules have greater energy added to them, they also tend to move around a lot more. So the entropy is also greater, and the potential to have a degradation or a generation of entropy, degradation of energy or generation of entropy, is greater when you're at a higher energy state. So that's related back to problem 1 on the exam. And then this disorganized energy is, it provides less useful work to us. So we have to be very careful about how we approach these systems and how we use them. Processes can't occur in any arbitrary direction. So the last lecture before the exam, we talked about the increase of entropy principle, which means that processes will occur in a certain direction, and previously we identified that they'll occur in the direction of decreasing quality of energy, or that it will go from hot to cold. Okay, so a process will naturally occur in the direction where the quality of the energy decreases. That just so happens to be the same direction as the increase in entropy. And it's not a conserved property. So you can't recover this entropy that you've generated. You can't somehow destroy it. That it's only conserved during ideal reversible processes where no entropy is generated in the first place. So in every other process that has any sort of inefficiency in it, entropy will be created. So we can't create mass, we can't create energy, but we do create entropy. And then these performance of engineering systems is degraded by this idea of entropy, or this process of irreversibility, that we cannot recover that energy that's lost, that once it's lost, it's gone forever, and there's no reversing that. For a reversible process, we know that the change in entropy is equal to this integral of del Q over T, so that was developed or theorized by Clausius. And for an irreversible process, it's equal to this integral of del Q over T plus some entropy generation. Okay, so again, a reversible process can be reversed. We can recover or go back to our original state, and any entropy that change that occurs during that reversible process can be reversed. So entropy would be conserved. But for an irreversible process, we always have this S-gen term, or this entropy that's generated during the process that we can't recover. Okay, so even if we go back to the initial state, there's going to be some entropy generated in the process from state 1 to 2, and for an irreversible process, again, from state 2 to 1. So even if we're operating on a cycle, we're returning to initial states, we're continuing to generate entropy throughout that process. And for an isolated system, we can look at this entropy generation as the total entropy change of both the system and the surroundings. Everybody's phones are going off. And the universe, of course, is considered an isolated system, so entropy generation of the universe is always present. And even though the entropy change of a system may decrease, if we take into account the entropy increase of the surroundings, we're going to have a positive number on that entropy generation. The entropy generation can never be negative. It can only be 0 or positive, whereas entropy change of an individual system can be negative, but if we were to calculate the entropy change of the surroundings, we would find that it was a positive number greater than or equal to the amount of entropy change of the system itself. Entropy is a property, so we can use the property tables to look it up, and we do have some entropy relations in terms of other property values. They're somewhat complicated relations, and they're not convenient to calculate over and over and over. So we have the tabulated values at our fingertips, and again, we treat them just like we would enthalpy or specific volume or internal energy, in that we calculate quality to find out the actual entropy of a saturated mixture. We can use the compressed liquid assumption, and then for a superheated vapor, we just need to know those two independent values to look up the value of entropy, just like any other property. We can change the entropy of a substance in a process two ways. One is by transferring heat to or from our system, or to or from the working fluid or the substance that we're concerned with. The other is through irreversibilities. Okay, so friction, head loss, chemical changes, any of those irreversibilities will contribute to the entropy change of a fixed substance. If the fixed substance does not have any entropy change, the process is called isentropic. Okay, so for a process that is reversible, meaning there's no friction, there's no head loss, there's no other chemical changes or contributions to irreversibility, if we consider it to be reversible, and adiabatic, which means what? No heat transfer, then we can say the process is isentropic. Okay, so this is another key word that you should memorize and look for in problem statements. That either the problem might explicitly say, during an isentropic process, which means you know that the entropy doesn't change, or they may say during a reversible adiabatic process, or a well-insulated reversible process, or some other words that would indicate there's no heat transfer involved, then you know the entropy doesn't change in that process. Okay, in most cases we're idealizing an actual process as isentropic, that it's very difficult in practice to achieve a process that is actually isentropic, though not entirely impossible. We can approximate and get really, really close. So an isentropic process is one where the net entropy change is 0, and in many cases we have adiabatic engineering processes. So we're insulating our turbines so that we have a maximum efficiency, or the boiler or the condenser, that in many cases we don't want heat transfer to other parts of our system. So they're well insulated, and that's a common way of increasing efficiency, is to prevent heat losses. And the isentropic assumption, again, allows for a best case scenario. So if we're approximating our system as adiabatic and reversible, then we're saying, okay, we don't have any losses due to heat transfer, and we don't have any other losses due to these other irreversibilities that we're concerned about. So we can see what the best case scenario would be for this actual process. So calculate the maximum work output or the minimum required work input is the isentropic case. And a process that is reversible and adiabatic will always be isentropic. However, isentropic does not necessarily mean that the process is reversible and adiabatic, because you can have a process with irreversibilities and heat transfer, which makes it an isentropic process. So let's say that you're losing some of your energy due to friction, but you're also adding heat to your system, that you're taking into account the loss of entropy, or the decrease in entropy due to these irreversibilities, and then either removing heat or adding heat, depending on if your process is an entropy loss or an entropy gain. So you can make a process isentropic even if it's not reversible and adiabatic by adding heat or or taking into account these irreversibilities in some other way, removing heat. Okay, so let's do an example of this. Steam enters an adiabatic turbine at 5 megapascals and 450 Celsius and leaves at a pressure of 1.4 megapascals. So let's determine the work output of the turbine per unit mass of steam if the process is reversible. So what are the two keywords in this problem that allow us to make a specific assumption? Okay, adiabatic and reversible. So when you see something that is adiabatic and reversible, you should automatically think isentropic. And isentropic means no change in entropy. Okay, so just like isothermal, isobaric, it's the same kind of thing. So entropy stays the same. Okay, so we have the initial conditions are set, right? P1 and T1 are known, so we can look up property values at P1 and T1. But at the second state, we only know the pressure. How do we fix the state in this problem? Yes, exactly. Okay, so state 1, we know P1 and T1. So P1 is 5 megapascals and T1 is 450 degrees Celsius. State 2, we know that P2 is 1.4 megapascals, and our second property value that we need to fix the state is that S2 is equal to S1. Okay, so that gives us two independent intensive properties to fix the state of state 2. Okay, so we can look at P1 and T1. So let's go to our book. If you have your book, get it out. It's good practice to use the property tables. We need more practice. At 5 megapascals and 450 degrees Celsius, what is our state? H. Okay, 3317.2. Where did you get that from? What table? Where are you? Is right. But where did you get it? Okay. So how do we find it? Okay, so it's table A6. At 5 megapascals and 450 Celsius, we're superheated. So we go to table A6, look in the column for 5 megapascals and the row for 450 Celsius, and we find H1 is equal to what? 3317.2 kilojoules per kilogram. Okay, what other property should we look up? S1 is what? 6.8210 kilojoules per kilogram Kelvin. So remember the units on that. We have temperature in the denominator. Okay, 6.8210 kilojoules per kilogram Kelvin. So then we can use that to fix the state at state 2. But how do we do that? So we have our pressure is 1.4 megapascals, and our entropy is 6.8210 kilojoules per kilogram Kelvin. So let's look on the superheated table at 1.4 megapascals. What's the lowest entropy on the table? Okay, 6.4675. If that number were higher than this value, we would know that we're not superheated anymore. But because this value is still within the superheated range at 1.4 megapascals, then we know we're still in table A6. We're still superheated state. If this were, let's say, instead of 6.82, just for example, let's say it were 6.32, where would we need to go? We have to go to the saturated table. So if we look at table A5, at 1.4 megapascals, we would be in the saturated liquid vapor mixture, So we would have to find the quality to find H2. Okay, but we're not there. We're still superheated. Okay, so how do we use this value to find H2? Okay, yeah, we'll have to interpolate. So by interpolation, we look for the values that are above and below 6.82, right? So we have 6.9553 and 6.748 kilojoules per kilogram Kelvin. And then we look on those same rows at the enthalpy values. So we have at the 6.9553 level, we have 3040.9 and 2927.9 kilojoules per kilogram. So we can say S1 minus, well, it doesn't matter which one we do. Okay, so S1 minus, we'll call this A and B, minus SA over SB minus SA is equal to, so S2. S2 minus SA over SB minus SA is equal to H2 minus HA over HB minus HA, and we're solving for H2. Okay, so we know all these other values. These are the A and the B values. We solve for H2, and we find that number to be 2967.4 kilojoules per kilogram, again by interpolation. Okay, so we find the property values at state 1, state 2. Ultimately, we want to find the work output of the turbine per unit mass. So per unit mass, we have all lowercase letters, Q in minus Q out plus work in minus work out is equal to H2 minus H1. So notice mass doesn't even factor into this equation. There's no mass flow rate. Do we have any heat transfer to or from our turbine? No, it's adiabatic. That was one of the assumptions from the beginning. And for a turbine, do we have work out or work in? Work out. So negative work out is equal to this H2 minus H1. And H2 happens to be less than H1, which works out perfectly for our sign. So work out is equal to this H1, 3317.2, minus H2, 2967.4 kilojoules per kilogram, which is 349.8 kilojoules per kilogram. So if we were to draw this on a TS diagram, what would it look like? So for plotting temperature and entropy, what would it look like? A box? A straight line. Okay, it could only be a box if it were a cycle. Has to be a single line. And is it up or down? What direction does it go? Down, okay, because our temperature is decreasing from T2 or T1 to T2. Okay, we're removing some of the energy from the steam. It's just a straight line down. An isentropic process on a TS diagram is going to be a single line like that. Okay. All right. So let's do another one. This time, instead of a turbine, we have a piston cylinder device that is heavily insulated, contains 0.05 meters cubed of steam at 300 kilopascals and 150 degrees Celsius. The steam is now compressed in a reversible manner to a pressure of 1 megapascal. Determine the work done on the steam during this process. All right, so can we fix state 1? We have a pressure of 300 kilopascals and a temperature of 150 degrees Celsius. What is our initial state? At 300 kilopascals and 150 Celsius, what's our state? Superheated, okay? So let's look up some property values. So we have P1, T1. We're going to need probably, let's see, for this piston cylinder device in a reversible manner. Right, okay. So we're going to need V1 and U1 and S1. So let's look those up. V1 is 0.63402 meters cubed per kilogram. U1 is 2571.0 and S1 is 7.0792 kilojoules per kilogram Kelvin, and then the units on U are of course kilojoules per kilogram. Why did I look up U instead of H? Okay, because it's a closed system. So let's perform an energy balance on this system. Q in minus Q out. Notice there's no dots above them because it's not a flowing system, it's a closed system. Plus work in minus work out is equal to M times U2 minus U1. So that's the equation, energy balance equation for a closed system. Do we have any heat transfer? Do we have any work interactions? Work in. Why is it work in? Okay, it's being compressed. Work's being done on the system. We have a work in, and then M times U2 minus U1. Let's say, for example, instead of a piston cylinder device, we had a rigid tank. Would we have any work interactions? No. If we had no heat transfer and there was no work on the system or by the system, then we would have that U2 is equal to U1, which means nothing happened, right? It hasn't changed. Okay, so if you don't add heat to a system, you don't do work on a system, then your internal energy won't change. But in this case, we're adding work to the system, so our internal energy must increase or decrease? Increase. So what's going to happen to the temperature of the system? It'll increase. Pressure, increase, okay? Because we're adding work to the system. This is not a frictionless piston cylinder device that's free to expand and compress with heat addition, which would mean the pressure would maintain constant. We're adding work to the system, which means the pressure and temperature will both change. Okay, we're given the final pressure, P2, is equal to 1 megapascal. How do we fix the second state? What other information do we know? Yeah, S2 is equal to S1, which we already looked up, is 7.0792 kilojoules per kilogram Kelvin. At this pressure and this entropy, do we have a superheated vapor or a saturated liquid vapor mix? And how do we figure that out? Yeah, it's superheated still. So if we look at the table for 1 megapascal, we can see that this value falls in the range of the entropy values on that table. So again, by interpolation, we can calculate or figure out some of these other terms. So in this case, we're going to look at U2 is equal to 2774.6 kilojoules per kilogram. So still table A6, again, table A6. So we know U2 and U1 from the tables. We don't know the mass. So we could calculate just the work per unit mass, but it doesn't say the specific work or the work per unit mass. We want to calculate the total work. Do we have a way of figuring out the mass? Yeah, so we have the volume, and we looked up the specific volume at the initial state. So the mass is equal to the total volume divided by the specific volume of state 1. The mass is not going to change, but the volume does change, which means the specific volume changes as well. So the volume over the mass is 0.05 meters cubed divided by 0.63402 meters cubed per kilogram. Gives us a mass of 0.0789 kilograms. So now we can plug everything into our equation. Work in is equal to this mass, 0.0789 kilograms, multiplied by U2, 2774.6, minus U1, 2571.0 kilojoules per kilogram, gives us 16.06 kilojoules for our final answer. And things are as we would expect, that the internal energy increased. If we were to, again, by interpolation, figure out the temperature of our final state, we'd find that it's higher than 150 degrees Celsius, corresponding to an increase in internal energy. Okay. Any questions on this example? Yeah. So on a TS diagram, we're now increasing temperature, but again, the entropy is remaining the same. So there's no increase in entropy, but the temperature is increasing. So again, still it's an isentropic process, it's a straight line, but now our temperature is increasing rather than decreasing.
Why do we use that particular balance?
Because it's a closed system. So if we look back to the derivation of the energy balance for an open system, it's because we have flow work. So the base energy equation is equal to the energy into the system minus the energy out of the system is equal to the change in energy of the system. Okay, so energy is coming in by heat and work, and energy is changing. The energy that is changing is represented by this change in internal energy. But for an open system, we now have energy coming into the system due to the mass that's flowing in, and the flow work is equal to PV. Okay, so there's mass coming in with some pressure and specific volume that's equal to the flow work. Okay, this term came up so many times that they decided to develop something called enthalpy, which is a combination property. So what enthalpy does is it moves the flow work from this side of the equation for an open system to the other side of the equation. So you have a U plus a PV term, which we then group is H. Okay, so for a closed system, there's no mass flow, so there's no flow work. So we use internal energy for a closed system. For an open system, we use H. There have been some exceptions with the piston cylinder device where we have come up with something similar, where if we have heat transfer and this boundary work, we can for a constant pressure process, we can say that this boundary work PV can combine with this U term over here on the other side of the equation to have an H in there, but that's a special case. We don't have constant pressure in this case, and there's no heat transfer, so we don't have anything else to balance out with a work term. So that's where that comes from. So the base energy equation is always this. For a closed system, you only have a change in internal energy. For an open system, you have a change in the enthalpy, which is the flow work included in it. Okay, let's do another example. I feel like talking through these is maybe more helpful than me just talking at you. Okay, and again, these are all types of problems you've done before. We've looked at pistons, we've looked at compressors, we've looked at turbines. If you always go back to the base fundamental rules of fixing the state and applying the correct energy equation, you can solve any problem. Okay? In theory, if you understand those fundamental principles, you should be able to solve any problem. You may have math errors, you may have other mistakes, but the thinking doesn't change, okay, on how to approach and solve these problems. So in this case, we have a compressor with R134A entering at 0 degrees Fahrenheit. Oh no, it's an English units problem. I should convert it to metric because I'm more familiar with that. No, just keep it in English units. We have tables for that. Okay, so R134A at 0 Fahrenheit. At the compressor exit, the specific entropy is the same as that at the inlet. What are they telling us? It's isentropic. Okay, in this case, they tell us explicitly the entropy doesn't change. They're not telling us necessarily that it's that there is no heat transfer. Determine the R134A exit temperature and the change in enthalpy of the R134A. Okay, so we know the inlet temperature and the inlet quality, saturated vapor, and we know the exit pressure. Okay, so if we go to our property tables for R134A, what table do we need to use? So 0 Fahrenheit, x equals 1. What table? Okay, so table A11E. Let's fix the state. State 1, A11E. We have a temperature of 0 degrees Fahrenheit. X is equal to 1. What is our enthalpy? H sub G, right? 103.1. Okay, what is our entropy? 0.22542. And what are the units on entropy? Oh yeah, why did I put kilojoules per kilogram? BTUs per pound mass. And this is BTUs per pound mass ranking. Okay. So state 2, we know the pressure is 60 psia. What is any other property value? Okay, S2 is equal to S1, so S2 is equal to this 0.22542 BTUs per pound mass ranking. How do we use that to find whatever else we want? And what table are we on? Okay, so let's go to the pressure table at 60 psia. So at 60 psia, what is S sub G? Yeah, bring your book. Okay, so at 60 psia, on the saturated liquid vapor tables, what is S sub G? 0.22 what? 132. Okay, is S sub G less than our value? Yeah. So what does that mean? Superheated. Okay, we're not saturated because we're higher than S sub G. If we were lower than S sub G and higher than S sub F, then we would be saturated. So we're not on the saturated liquid vapor table, which means we need to go to the superheated vapor table. So S2 at 60 psia, we look in the columns and we try to find where the value, 0.22542, is sort of in between everything. So we find that in between the saturation temperature and 60 Fahrenheit is where we lie. So we're somewhere in between 49 Fahrenheit and 60 Fahrenheit, pretty close to 60 Fahrenheit, right? So at 49.84, we have 0.22132, and at 60, we have 0.22572 kilojoule, no, not kilojoules, BTU per pound mass. See, even I want to do that, pound mass ranking. Okay, so again, by interpolation, between those two values, using the same method we've used before, we find that our S2 lies between those two and is pretty close to 60. So T2 is 59.3 degrees Fahrenheit. So we found the exit temperature. We can follow a similar approach to find the enthalpy of state 2, H2, and this, just as a note, that my property values are slightly different from the ones that are in this table because the older edition is what I based this example off of before. So it'll be very close, but if it's not exact, don't freak out. 112.23 BTU per pound mass. So then we calculate delta H to be 9.15 BTUs per pound mass. Yeah, you have to also interpolate to find H2. So you'd have to look up the H value at Tsat. So the H there is 110.13, and the H value here is 112.39 BTUs per pound mass. So you follow the same methodology to interpolate, and you find a value that's in between the two, close to this value because we're close to this value. And then when you calculate the difference, you get 9.15 BTUs per pound mass. If you don't know how to interpolate by this point, you need to learn. Mm-hmm. Yeah, it's fine. As long as you know how to do it. Yeah. No, and as long as you say, like, by interpolation. I get really suspicious when just random values show up on papers that perfectly match the solution. So if you've done it by interpolation, you don't have to show all that work if you have a calculator that does it. You don't need to spend all that time doing it. Make sure you're doing it correctly, and always double check to say, okay, I should be in between these two values. If you get some weird value that's outside that range, you've done your interpolation wrong. You put stuff in your calculator wrong. So it's good to always have that understanding of how it works so that you know when you get a really wrong answer. Okay. So we've talked about the TS diagram and how in the isentropic case it's just simply a straight line. So again, on this one it would be similar. In this case, our temperature is increasing for this problem, this example compressor problem that we just did. So it would look the same though, it would be just a straight line. What's useful to us is that similar to a PV diagram where the area under the PV curve is what? On a PV diagram, the area under the curve is the work. Okay, so on a TS diagram, the area under the curve is the heat transfer or the reversible heat transfer. So it's very similar idea. And another useful way to, at a glance, look at a property diagram for two different systems and determine which one is less reversible. Well, if this one has more heat transfer, which is undesirable, then I don't want to go with this one. Or maybe heat transfer is the goal, and so you're trying to maximize heat transfer, like if you're trying to remove heat from a system or add heat to a system for some other purpose, then you could also look at a TS diagram and compare different processes to see which one is better for your application. So if it's an isothermal, internally reversible process where the temperature is constant, then it would just show up as a straight line. And you could calculate Q very easily as the area under that curve. Okay, so Q would just be delta S times T. Okay, that only works for an isothermal process, that it's delta S times T. For an isentropic process, you would have no heat transfer, or Q would be equal to 0. So the area under the curve is 0. So let's just do some examples where we calculate the area under the curve. And you have one problem like this on your homework, so it's important to understand how it works. But it's similar to what we've done previously with PV diagrams. And it's just basic geometry, so hopefully it makes sense to you. But if we have a two-step process where we're going from state 1 to state 2, our entropy is increasing, what do you think that means is happening to our system? If our entropy is increasing. Okay, the quality of energy is less, right? No, opposite. that we're moving to a higher energy state, so the quality is higher, but it's more disorganized. Okay, so we're adding entropy to the system, or our entropy is increasing, so what must we be doing? Maybe I'm not asking the question in a good way. We're adding heat. Yeah, that's the answer I'm looking for. Okay, so if we're increasing in entropy, it means we're adding heat. So in this case, the temperature is increasing, the entropy is increasing. We're adding heat to our system from state 1 to 2. So we can calculate this in two segments. From state 2 to 3, then, what is happening to our system? Okay, the temperature is maintained as a constant value, but the entropy is increasing. Okay, so we are possibly removing heat, like during a compression process. You can maintain an isothermal process by removing heat as you compress it. That may be what's happening here. They don't say specifically. So to calculate the area under the curve, we first have a positive area. So Q is equal to Q from 1 to 2 plus Q from 2 to 3. Okay, so, and note that this is in BTUs per pound mass times Rankine. We don't know the mass of this system, so we're doing it all in terms of specific values. So Q from 1 to 2 is equal to the integral of T ds from 1 to 2 and the integral from 2 to 3 of T ds for the second part of it. We don't know the functional relationship. We don't actually have to calculate this integral, but numerically we can calculate the area under the curve, which is what an integral represents because it's linear. So we can calculate the area under the curve for those two cases. Important to note that we want this in terms of absolute temperature units, so we would convert to the absolute temperature. And from Fahrenheit, it's easiest to just convert to Rankine. So the area of part 1 would be 55 plus 460 to convert to Rankine, plus 360 plus 460, again converting to Rankine. So this is T1 plus T2 over 2 multiplied by that delta S from 1 to 2, which is 3.0 minus 1.0 BTUs per pound mass Rankine, and then this is Rankine. So that's Q from 1 to 2. So the value we find for that is 1,335. BTUs per pound mass. Then we have to subtract off the area from 2 to 3, which is just a rectangle. So we have this, again, 360 plus 460. So that's the temperature of state 2 and state 3, 360 plus 460 Rankine, times 2.0 minus 3.0. So the minus sign takes care of itself if we're going in the proper direction. So we find this is 820 BTUs per pound mass. So if we add them together, actually negative 820, so 1335 minus 820, so then the total Q is equal to 515 BTUs per pound mass. Okay, so we've calculated a positive area and a negative area to get our total value. Okay, we could do the same thing on this problem. So from 1 to 2, are we adding heat or removing heat? Removing heat, and 2 to 3, adding it. Okay, so we could perform a similar analysis where we calculate the area, and you can do this on your own, that you'll get 140 kilojoules per kilogram. And I'll let you just play with that. Yeah. Sometimes processes have that that result if you're also compressing. So you can be compressing, temperature will be increasing, but you're also removing some of the heat, not all. So it is possible to remove heat and increase in temperature, but good catch. So I don't know, this is an imaginary thing. I don't even know what the process specifically is. We just know on the TS diagram. Okay. So negative, positive, we'll go. So if we look at a TS diagram, you can see all the lines. So this is the saturated liquid vapor mixture dome, and this diagram's in your book. And then these, it's difficult to see on here, but the lines on this side are temperature and entropy. The ones going this way, I think, are pressure, and the ones going this way are specific volume. It's easier to see in your book. This diagram is useful to look at just to get an overall view of what happens to increase the, if you increase the entropy, where do you move on the diagram, things like that. In practice, it's not very practical to use this diagram to try to pinpoint, especially over in this region, to try to find exact values is quite difficult. But it just gives you an idea that the dome still exists. It's still a property diagram. We can still look at how changing the temperature, changing the entropy, moving the specific volume, how that affects where we are on the dome. And then, of course, that far left region is just the impossible region, meaning you can't have that combination of temperature and entropy. A Mollier diagram is a very useful diagram because we plot entropy and enthalpy. So in essence, what you're looking at is the relationship between the work, represented by a change in enthalpy, and the irreversibilities, which is represented by a change in entropy. So the Mollier diagram, again, for water, they have this diagram in the book, and it's super tiny and kind of useless. But I think it's more just as an example to see what it looks like. Again, we see the dome, but now the dome has kind of shifted and it's offset and it's there instead. So the Mollier diagram, this one, not quite so useful, but if you were to plot your process and show your change in enthalpy, your change in entropy, you could see how much relative work is being done versus the irreversibilities in the system. And if you compare multiple processes, one to another, then again, at a glance, you can look and see, okay, I'm getting the most work out of this one with fewer irreversibilities. That's the one I want to go with as you go through the design process. So let's just plot one last property diagram to test our understanding of how it works, how enthalpy and entropy are related. So this is the Carnot cycle, the reversible Carnot cycle, that from state 1 to 2, we have reversible isothermal expansion. Okay, so if it's an isothermal expansion process, what do we kind of know about our system and maybe what's happening in that process? Okay, why is it a horizontal line? Okay, so it's isothermal, it's going to be a horizontal line. And if we're expanding, is the entropy increasing or decreasing? Decreasing? Okay, so if we're expanding in a normal process, let's forget the isothermal. If we're expanding a fluid, what's going to happen to the temperature of it? It's going to decrease, right? Okay, so but it's isothermal. Okay, so that's the key there. That if in order to keep a process isothermal when we are expanding, what do we have to do? Add heat. Add heat. Okay, because just a normal expansion process, let's just say piston cylinder device, it's free to expand. That the temperature would decrease, right? Or not free to expand, we're forcing it to expand. Then the temperature would naturally decrease. So to keep it at an isothermal case, we have to add heat. And if we're adding heat, what happens to the entropy? It increases. Okay, so if we start out here at state 1 and we perform a reversible isothermal expansion, it means we're adding heat and our entropy is increasing. Right? Can we agree on that? Okay, now reversible adiabatic expansion. Okay, it's reversible and adiabatic, so it has to be isentropic. Okay, it's going to be a straight line, and it's an expansion process. So what's happening to the temperature? It's decreasing, right? Because we're not adding any heat to it now. It's adiabatic. It's going to be a straight line down. Okay, so that's state 3. Then we do reversible isothermal compression. So what does isothermal compression look like? Okay, there's no temperature change. Temperature is constant, so it's a straight line. Is it going this way or this way? Why would it be going this way? We'd have to remove heat, which means we're decreasing the entropy. Okay, so from state 3 to 4, and then reversible adiabatic. This is QH, this is QL. Reversible adiabatic compression. Okay, there's no heat transfer. It's isentropic. We could pretty much figure it's going to go back to 1 because we know it's a cycle. But if we didn't know that, we'd think, okay, it's a compression process. I'm not removing any heat or adding any heat. If I'm compressing a gas, what happens to the temperature? It increases. Okay, so it goes back up. So this is the Carnot cycle on a TS diagram. And it's useful to know how to plot that. Okay, any questions? All right.